Okay. So hello everybody. This talk will be 5 years of bad ideas. So I'm doing Python for I think close to 5 years now, or maybe even a little bit longer. And Georg and I, and Georg is the main developer behind Sphinx, the documentation tool, we sort of started exploring things you can do with Python over the last couple of 5 years, which are non-obvious, I suppose. So first, a general idea of what defines Python. Python has a couple of core values. One of them is beautiful code, the low-clutter syntax, and everything is a first-class object, including functions and types, functions and classes. And while there are differences between built-in types and things you define yourself, they're close enough that you wouldn't mind too much about the differences between those two. But Python does a little bit more. You have the ability to evaluate code at runtime, and you get a lot of access to interpreter internals you're probably not supposed to deal with. And Python also, however, has a community that doesn't really embrace the idea of monkey patching, even though it's possible. So while we can do monkey patches, we usually choose to not monkey patch for a more beautiful solution. And this is unlike the Ruby community, for instance, where, if anyone remembers Seth Shaw, one of the people that are now doing a lot of Python code, he came from the Ruby community. And a couple of days ago, I had a heated discussion with him on Twitter about magic in Python. And this was one of the tweets that he was, as a result of the discussion, was tweeting out. And honestly, I only find this shit in web frameworks. What the fuck is up with Python people going ballistic when a web app uses magic? Bullshit. So he was encouraging people to do more magic. So this talk will be entirely made of magic. So what is magic? So first of all, certain things require magic in Python. For example, if you have used Python's pyramid or one of the Werkzeug based on one of the frameworks based on Werkzeug, if you get an exception, you're usually dropping into an in-browser traceback debugger where you can evaluate code. This wouldn't work without magic. Generally, stepping through code with a debugger deals with a lot of Python internals. And if you have generated code and you want your line numbers to match up perfectly, you really need to dive very deep into the internals of the Python interpreter. And generated code in general means you are dealing with things people normally don't deal with. So magic is fine for as long as it's not required. And magic becomes a burden if it ends up in production code and suddenly fails in very interesting ways. So I divided this talk into multiple categories of magic, and the first one is common magic, and this involves dealing with sysgetFrame. So what sysgetFrame does, if you call it, you get an object back, which is an interpreter frame. And this frame object gives you access to a lot of stuff, which can be useful. For instance, the line number. So if you call sysgetFrame and you give it a 1 as an argument, it means give me the frame of the scope 1 level up. And you get the frame object of the calling code in this case. And then you can figure out what line number the code is in, from what file name you're calling this. And this gives you a nice way to debug code by just calling in and you know where the caller came from. This is how a logging, for instance, figures out where a log call came from. But you can do a lot more with sysgetFrame. So for instance, if you have used SOAP interfaces, there's a function called implements. And you can pass it a number of interfaces. And I don't know how SOAP interfaces are implemented, but this is a way you can implement them. You get the frame of the calling code, and you get the flocals object, which is a dictionary with all local variables. And coming from a class frame, it means you can also modify this. And what you can do, you can see if there's a meta class in there, which is specified by under meta class. And if there is no meta class in there, you patch in your own one. And you make up this meta class by creating a meta class on the fly for this particular interfaces, and you can extend or redefine the way Python does method resolution ordering. You can sort of hook into the class creation process without having to expose people to the fact that there's a meta class involved. The following example here comes from, I think, Nat Bachelda's talk. I don't know where it came from originally, but I know it was at PyCon. A way to get access to the Django request object in a very weird way. You get the current frame and you go as many frames up as it needs to find until it finds a local variable named request, which has an attribute called meta. And if you do this on PyPy, you will basically make sure that your code is really, really slow because the JIT interpreter has to stop working at that point. Meta classes in general are an amazing way to sort of extend behavior in places where people wouldn't expect them. So because a meta class is essentially the class of a class, you can change the behavior of how a class works. So you can change the behavior. You can get rid of constructors and replace them with something else, or you can define operators for your own classes. So, for instance, the class AwesomeDays here has an getItem operator, where you can look up the subclasses of that class by name, if you choose to do that. Exec compile. With exec, you can execute a code object. With compile, you can convert string into a code object. And if you give exec just a string, it will automatically compile this for you. And because exec allows you to execute code in a specific frame and not necessarily the callers frame, you can execute code against an empty dictionary and then look into the dictionary for change. So for instance, you can use this to get a function from any arbitrary file. So you use, in this case I was using exec file, but you can also just use exec. So it will execute the file hello.cfg, which means configuration in this case, and it will look up a function called main there and then call this. And this is completely isolated from any other module in your Python interpreter. Another reason why this is magic is because this module in there doesn't have a name. So if you execute hello.cfg, it will not have a name, it will not have an entry in sys.modules. And as a result of that, every code that relies on the fact that there is a name for the module will fail. So you can't pickle any classes in there, for instance. Because the way pickle works, it says, okay, your class is a canonical name. It's the module name plus the class name. But this is not a module, it's just executed Python code. The ASD was introduced in Python 2.5, and in Python 2.6 you can compile it. AST stands for Abstract Syntax Tree, and what you can do is you can look at your Python source code in a way that makes sense for a compiler. So, for instance, instead of saying A equals 1 plus 2, it would be assign A to a binary at between 1 and 2. And if you parse a string into an AST, you can modify the operators. So for instance, in this case, I'm changing 1 plus 2 into 1 minus 2, and if you evaluate this, it will return a different result. And with a little bit of extra magic, you can use this to change modules on the fly as you need them. And this is actually useful. So for instance, coupled with an import hook, you could rewrite assert statements into better expressions for test suites, which, as far as I understand, PyTest is doing currently, or at least in a branch. You can use this to implement list-style macros, and you can use this, of course, for code generation. And this is an example from a project that Georg did called Canicle. And what you do, the first two functions here have to go into a separate file for this magic to work. But essentially what it does is, if you use the decorator macro on a function, and you then use the function in a module, it will apply some magic and then replace the function body where it's defined. So the doing something function will not call add 1 and 2, it will instead replace the add function with 1 plus 2. And the under body for the with statement is replaced by the actual print iterating statement. And you can, this way, extend the language as much as you want. And of course, you should do this in production code, although some people do. Import hooks in general are amazing. So this is actually a working example. I wrote a module called GitHub Importer, And what it does is it acts as a path hook, which means you have, in sys.path, you have a bunch of entries, and each of them is a string. You can encode in this string your own personal information for your own path hook, how to deal with an import. So for instance, if I install the GitHub importer path hook, and I add a path called github://username/project, it will check on GitHub in this particular repository if there is a module named Ginger2 if you import it. And sure enough, you can actually import Ginger2 directly from GitHub. It will be amazingly slow because Ginger2 sort of imports it all itself from multiple files in the under init because it needs all of its functions at any point anyways, so there is no reason to have to spread it to multiple modules. And the way the Python import system works, it tries more file names than there is necessary. So it will trigger around 500 HTTP requests, so it might take a while. Monkey patching, in general, is something people don't do, but you can do. You can just monkey patch any arbitrary function on any object. But what makes monkey patching really interesting in Python is the only place where you need to do monkey patching, which is a patch under built-in. So under built-in is the one module where Python looks for names it really has no idea about how to find in a file. So for instance, if you call the store list function, for instance, which is a type actually, the way it finds it, it notices, okay, there is no local variable named list, there is no variable named list in the whole file, so it falls back to the under built-in module. In fact, there is a more complex logic behind it, but if you change something on built-in, you're pretty much guaranteed that you will not need to import your code. And this is, I don't know if it's still in the documentation, but this was actually supported, I think at one point, that you replace, if you set underscore on built-in to your own getEx function, and without having to do any import, you can just underscore and then in parentheses a string, and it will be translated to the language of choice. And the problem with this particular monkey patch is that if you're in an interactive interpreter and there is a result of an expression, it will overwrite this particular monkey patch because the last result of an expression is always assigned to the underscore. So if you ever do this in your code, don't use the interactive shell. But there is another reason why people monkey patch under built-in, which is the under import function, which is guaranteed to be used for imports. While there are import hooks, there are a couple of really weird magical tricks you might want to do, which are not supported by import hooks. So this is your gateway drug. Uncommon magic. Now this is where I think gets really horrible. Sys.modules is where Python caches its imports. And the way an import in Python works, first of all, if you import a module named foo, it will check in sysmodules if there is an entry. And the entry is not none. So if there is an entry in there, it will return that. But if you check in an executed module, if there is an entry in sys.modules for yourself, at the top of the file, you will notice you're already in sys.modules when you execute it. So Python, the first thing after finding a module, it will create an entry in sysmodules and then executing the code in there, which opens a really, really neat trick. You can replace the module in place, which many people do. So for example, you can create your own magic module, which has a global variable, which is not really a global variable, it's actually a property on the module object called git_hash. So if you import from your magic module git_hash, it will look into the file system and try to find the git reference master hash and return that. Which sort of makes sense, I guess, because it's something you usually don't want to do except for debugging, and it's just a global variable, so it's nice. The downside is it becomes a little bit tricky with reference counting, so your module doesn't clean up properly. But I suppose that's fine. And it works, so you can just import magic module, and it has a git hash attribute. And you can also do from magic module but git hash, and it will still work. So someone today asked how to do, why Python has case-sensitive variables. Well, with custom namespaces, you don't need to. You can create your own mutable mapping, which converts every access to lowercase, and if you are the controller of your executed code, you can surely enough have case-insensitive variables if you really want to do that. And if you pair this with an import hook, I'm pretty sure you might be able to do this with general modules. Downside, it doesn't work for attributes. but at least for global variables and local variables. Code reloading. This is something many people try to attempt, and it's surprisingly hard to do. I have an implementation, a blocking system called Sign or Scene. And the idea is that if you have a plugin, and this plugin changes, you don't want to restart your web server for the plugin changes to appear. But you still want your plugin to be implemented as a standard Python package. So what can you do? Well, first of all, you have to design the application for reloading, which means the application has to sort of be aware of the fact that stuff goes away randomly. And then you have to make sure that there is some sort of global lock. So in Sign, for instance, when a request comes in, it checks if the lock is held. And if the lock is held, it means someone is reloading your code. And then what you do is you purge all entries from sys.modules, which depend on each other, and on this plugin, and then you reload the plugin. And it works. But then again, it means the whole world stops for while you're reloading code. And if this module was monkey patching something on another module, you will never find out. And you have amazingly memory leaks. Multi-versioning. So if you really want to have multiple versions of the same library loaded, that doesn't work in Python. Unless you monkey patch built in and put your own import functionality on there. So the idea is a library is a standard Python module, so you want to have the standard behavior sort of still in place if you do multi-versioning. And modules are cached in sys.modules, so we can't do anything about that. So how can we deal with the problem? Well, import hooks are good, but they don't support what we want to do. So we have to monkey patch under the import. And what under the import can do is, first of all, it gets a global dictionary passed in anyways. But if someone calls under the import by hand, we can use sys.getFrame to find the call's global dictionary. And then we can find information be carefully placed in this global dictionary if the caller was requesting a particular version of the library. So the implementation you really don't want to know, but if you want, it's on github/mitsuhiko/multi-versioning. And what it does is you import multi-versioning module, and then you call require. And then you provide the name of the library and the version you're interested in. And then if it next time to import mylib from this particular module, you will get version 2.0 of mylib. And if you check in the interactive interpreter how it works, well, it will rename the module in place to multi-version space mylib under, and then binary encoded version number, and then mylib. And from the, it will also, because many people are under impression that after import there will be an entry in sys modules for mylib, it will insert a proxy in there. So if you access the proxy, it calls sys.getFrame again to figure out where you're coming from and so on. And it works surprisingly well, actually. And then there's interpreter warfare, when you're doing... So everything up to that point can be justified by it works because the language works that way, and it's sort of documented behavior. And this is where this sort of stops being the case. So if you have generated code, and at one point you want to have all local variables there, and some of these local variables might be in higher function, in an outer function, what you can do is you can if 0, and then call a function that's not there and mention all of these variables, and locals will return that. Which actually Ginger2 is doing on CPython if it needs to expose you to... so if you're interested in what variables are defined in a scope, Ginger2 can sort of give you the information of all variables that are there at one point. So it doesn't have to track the context itself. So, but this, of course, relies on the idea that the Python interpreter is creating the closures before it's removing unused code. Because if you check the bytecode, there is no mention of if 0 in there, because it knows, oh, this will never be executed. So don't do that. Patching tracebacks, which is something I was sort of very proud of when I figured this out the first time. So the problem is that the way Ginger2 works, it generates Python code. And of course, the line numbers in the generated Python code will be vastly different from the line numbers in the template file. So what happens if you get an exception? Well, it points to a random line number in generated code you have no idea about. So what Ginger2 is doing, it keeps a key value pair of all line numbers that might be exceptions and the line numbers in the original file. So if I get an exception, I change the line number for all exceptions for this particular frame, traceback frame, and rewrite the exception. Now the problem is you can't change anything on there. And Ginger 2 also wants to hide frames from you which are deep in the internal stack. So what it's doing, it's rewriting made-up exceptions from made-up locations, and then it wants to mingle those together. But it turns out you can't change TB next, which is sort of the reference to the next frame object in Python. Well, what you can do is you can import C-types and create your own Python struct, which is the built-in Python struct for all objects, and you have to make sure that those work for debug builds, which unfortunately I messed up and it crashes on Spark machines, but I fixed that. And then what you can do, you can recreate your own traceback object. And then you have a function which takes the address of this traceback object, creates this C-type struct of it. So you have an actual byte representation. You have a C-type struct of what's in the Python interpreter, and you can change the linking. And you can also change the reference count. Because you can do that because you know you own the reference, so you never will trigger the deallocator at that point. Because if you would do that, you would crash because something doesn't hold the GIL or GIL. So it works. But this is magic that's only in place during debugging. So in a production system, you will not see this code being run. But this is the sort of magic that makes people like Ginger, because it gives you the correct line numbers if you mess up in templates. This here is a neat trick that Georg found. Because Python has a garbage collector, and the garbage collector has an internal graph of which objects are available to any other object, or which sort of depend on each other. What you can do is you can get the frame, and with the frame you can go to stack up to the first calls to the topmost stack frame. Make sure you have an flocus dictionary created for each of these stacks. So the reason why flocus here has to be accessed in this line over here is because by default Python will not create a dictionary for a local frame. It will do some internal optimization of not creating dictionary. But if you create one, it's cached for until I think next time it's modified. And then you can get the referrers of any object, and if that referrer is a dictionary, you know the object is found in the dictionary, and you just have to go through all items in the dictionary, and then you can find out the key. And this way you can find out that the list A has the names A and B. I don't think it's useful, and it's pretty damn slow. But you can also do this sort of hackery on bytecode level. So with this handy little function, you can disassemble bytecode into the opcode and the argument. And this one is not handling extended arguments, but that's unnecessary for the following hack, where we want to get rid of the self first parameter on functions. So we want to subclass something called implicit self, and if we do that, we don't want to mention self in as first argument to the function. And the way we can do this is we write a function called inject self, and it goes through the bytecode of your function code basically, and it finds if there is a load. First of all, we have to inject a first parameter into the function because it will be the first parameter. As a result of that, every other variable will shift away to a new location because self has to be the first one. So we have to sort of get a new dictionary or a new mapping of all variables and now the local indices for these variables. And then we have to check every opcode that operates on names and rewrite that. And we have to make sure that self was previously used as a global variable because it was never defined. So we have to change that to local fast variables. And then we can create a simple meta class which really doesn't have to do anything besides getting the function called the old one, creating a new one, extending the argument count by 1, extending the number of local variables by 1, and then in the constructor of the meta class we can, for every function, do this funky monkey patch, and it works. If you have used PHP, there is a function called return value used. And the idea is that you change the behavior of a function based on the idea of if your caller discards the return value or not. So for example, you could write a function called, I don't know, menu item, which will return HTML string if you take it, or it will print it if you're not interested in the return value. This is also sort of how some other languages work, like MATLAB, for instance. You can have function work differently depending on the return value. And in Perl, you can even do this based on the type of the variable that's after your function call. So in this case, we want to do this menu item. We get all menu items, render them to HTML. If the return value is used, return the HTML, otherwise we print it. So, which obviously can only be used for CGI applications, so which is where this code should go. So the way it works, we're calling the caller's caller, we're getting the frame of the caller's caller, and then frame last I is the last executed bytecode instruction. And then we have to check if this instruction has an argument, and based on this we can figure out what the next instruction will be. And if the next instruction is pop top, which means I'm not interested in your return value, basically, we know that the return value is used. Otherwise, we know that someone deals with this return value. And based on this function, we can further extend this and figure out what the return value, the name of the resulting value will be. So, for instance, you can have a module where the name is the assigned name, and if you assign this module to admin, the name is actually admin. And this works pretty much the same. All we have to do is to figure out the next bytecode instruction, get its argument, check the argument against the number of the names we know, and then we can figure out what the name is. And all of this here is actually implemented, so let's see if this works. Okay. So let me just see if I can split the screen, it's easier. Okay. So for instance, the assigned name here, in this example, we can, so in name tuple you really have to duplicate the name, which you want to have both for the variable you assign to, and then you also have to pass it to the constructor of name tuple. In this case, what we can do is we can here say, token is a name tuple, and the first argument is implied by the assigned name, and fair enough, this works. So it figures out the name of token by the assigned, where it's assigned to. And this is what I actually wanted to show, is the GitHub importer, which imports, in this case, markup safe, because Ginger is way too large. And if the network plays well, which I really hope it does. But it is slow, so that's not surprising. It's very slow. So if it would finish, it would print that the name of the imported function is github//mitsuhiko/ markup safe/ under init.py, and it will run the executed code. But I suppose.
Is there no black magic to make the internet work?
Apparently not. Yeah, so this probably won't finish. And the multi-versioning is here, where this might actually be the only one that's actually useful in this presentation, just for experimentation purposes. So this application here is called example.py, and it imports multi-version and requires the library mylib in version 1.0. And then it imports it and prints out the version. And then it has another module which requires version 2.0, imports it and uses it. And the way it finds the particular versions is it looks for mylib dash the version, and inside this it will have the regular module. And if you execute this, if you execute this, you will see that it does the name angling. Here it imports mylib in main in version 1.0, and this is the actual path that ends up being used. So it's a vastly different path. And in the other module, it will use version 2.0. Which I personally really would love to see if someone comes up with a clean implementation of this, which actually works in Python. Because you might really end up in a situation where you need SQL alchemy in two different versions. but the C algorithm changes API every once in a while. No longer, fortunately, but until version 0.4, you always had this problem that there was a deprecation warning all over the place. Okay, so I'm actually running short, so I would probably open for questions. With Mike.
With what's my name, if they do any math on the resulting expression, then you're not going to get the right result, are you? So if they say, they call your function, and then they say plus ABCDE in a string, then you're not going to know about that ABCDE, are you?
Yeah, I was hoping someone would miss this. It also feels horrible if you assign to an expression that's like a tuple, or have A, comma, B something. And yes, of course, if you want to go this route down to I don't know, to every possible way, you would have to evaluate the bytecodes. You have to figure out where the next bytecode instruction is, really. But I was hoping that's not something you would actually have as a problem. Yes. You wouldn't use this module in the first place.
Are these code samples going to be made available?
Yes, all these code examples will be on GitHub/mitsuhiko/badideas, and the slides will be at this particular location. So you will find them there shortly after the talk.
Any other question?
Now, I think you are a very, very, very bad boy, and I don't know if you're a Ruby spy or something. But I remember from a couple of years ago there were a few projects for something like MetaPython or things that make it more Lisp-y. And I don't know how it's the state now. It's gone somewhere in experimentations with MPyPy or something that could make this magic just seem...
The problem with this magic is the magic, not necessarily the implementation, even though the implementation is horrible. But the AST module, with the AST module in place, you don't need any more magic in Python, because what you can do, you can actually sort of mostly reliable with combined with an import hook, rewrite any Python code in place. And even though it is magic, there are reasons why you sometimes might want to do this. So debugging comes in mind. So you can use the AST module to intercept certain expressions, and you can also use the AST module, which makes more sense, to figure out if you have, like, you can statically go over your code and find constructs which might be problematic. Like, I don't know, I'm personally using the AST module, for instance, for backwards incompatible upgrades, similar to the 223 module, where I go over code and see if you're using the old name of function, and I give you a diff and say, at this particular place, there is a new function in place. I wouldn't necessarily recommend doing this at runtime unless you're a testing tool, where you really want to provide as much debugging information as possible at runtime.
It can help with static code inspection as well, I suppose, so much.
I didn't get the question.
Debugging, not just in runtime debugging or testing the static code analysis.
Yeah, this is PyFlakes, I think, is using the AST module also to figure out missing imports and all this. So there are use cases for this, but I don't think, if there is such a thing as a MetaPy, I wouldn't recommend reviving it for the sake of keeping people's code magic-free.
Any other question? There.
Waiting for the mic. Thank you for your talk, Armin. First thing is pajamas, which is quite a big application that uses AST manipulation, as I recall. And if you'd like to say something about that. And the other thing is, it sort of does bother me a bit sometimes that sys.doc modules is a global object. You know, global objects are bad. And we have Well, we have one of them, which I suppose is sys.modules are necessarily evil.
I was actually trying last year Python to get rid of sys.modules, and it turns out everybody relies on how it works. The problem is that the under and the import function in Python has a really, really weird API based on the fact that you were never supposed to call it yourself. So if you run import sys, it will call under import and then just sys and then a bunch of other arguments. But if you import something from within a package, the whole invocation of this path looks really different. So what people started doing is just calling import on the module and then looking up the actual module in sys.modules instead of taking advantage of the return value of the import statement. So because of that, this is also with importlib, this is the official way how to import modules. So everybody is relying left and right on the existing behavior of sys.modules. And this is why this particular multi-versioning stuff has all the information in sys.modules. Also, you wouldn't be completely able to get rid of sys.modules because you want them to be cached somewhere, but you might be able to make the key of sys.modules actually a tuple, where the first one is the name of the module, the second one is, for instance, a version identifier. But it would break too many people code, so that's something for Python 4, I suppose. When it comes to pajamas, I haven't looked at the implementation, but I think it might predate the current AST module, because there was an AST module, it was called the compiler package in Python 2.4 and earlier, which was based on the same parser, but it was a pure Python implementation. And this is what pajamas might still be using. And there is no reason why you should. So pajamas is, as far as I understand, turning Python code into JavaScript.
Yeah.
And if you apply enough magic on this, it might actually work. So for example, GWT is doing the same thing for Java. There is an implementation of XNA, which is a game development kit for .NET, which is taking the like sort of meta language between the parsing of C# codes and generating native codes. Is like the equivalent of bytecode of .NET, and turns this into JavaScript code. And this might actually be the better idea. Instead of taking the AST and turning it into JavaScript to implement a sort of virtual machine or a translator between bytecode and JavaScript. But as far as I understand, pajamas works perfectly fine, so there's probably no reason not to use AST there. It is smashing in the first place, so it's hard to say. I haven't used it. I know that the Java and the C# versions, which are implemented differently, as far as I understand, are widely used by people. So if AST is what's needed to make this work for Python 2, I don't see a reason not to use it.
Any question?
How stable is this kind of magic across different versions of Python? You're looking into internals, so they're not, basically anything could change without even being documented, or it's not like you're using the official API. So when you're looking, especially when you're looking at the bytecode internals and something like that, do you have to review the internals often and change the stuff so that it works when a new Python version comes out or anything?
So the multi-version is actually surprisingly reasonable in terms of implementation, in that the only thing it does is using APIs that are sort of sanctioned as being public. The only exception might be the hack with sysgetFrame to get, so there are two places where it has to call sysgetFrame. If you import if you execute this particular piece of code, what's happening behind the lines is, oh, this is a bad idea. multi-version mapping, I think. Yeah, it creates a dictionary there where it keeps the information that mylib is in version 1.0. So this requires one call to sysgetFrame, which is bad idea. But so far it's the API you want to use. Now if you do an import for mylib, the print here is from the module itself. This sort of causes a small problem. It doesn't cause a problem because all I'm using here is documented API, with the only exception that I'm renaming the module in place, which is something Python code doesn't think I would be doing. But the problem is if I call import myself this way. If I call import this way, it will still work. But what happens behind the scenes is it will see, okay, you forgot to something called this function and did not provide a global dictionary. Because normally if Python calls this function, it will call it globals, locals, or the other way around, I don't know. And I don't know if it's none or an empty list or something else. So this is what normally is happening. So because in the call above here, I'm not providing globals, it has to use sysgetFrame. And this is the point where this whole hack falls apart, because importlib will also call import yourself. It will call import for you. And because it calls import for you, and without global dictionary, I will get the global dictionary of importlib instead of the global dictionary of my own code. So if someone would really want to use this in practice, one would have to know every module which does import magic and explicitly whitelist this. So this is where this whole thing falls apart. And the other problem is if I importlib, if I get into sys modules for mylib, what's in there is a weak proxy to a module proxy, and the module proxy then looks into sysgetFrame and figures out where this call is coming from. Because if I'm doing version here, what happens behind the scenes is that get attribute operator has to call sysgetFrame to figure out what's my calling frame, and then get there the global dictionary called multi-version mapping to figure out where it's coming from. But I was sort of expecting it to be way worse, and it actually uses sort of official API. So if in the Python language specification, someone would I don't know, deprecate under import and make importlib the official version to import modules, you can probably do that, because then you can extend or change the behavior of the language without breaking too much code. And then you could also, I don't know, you probably wouldn't need this weird magic rename thing. Yeah, but I don't know. I wouldn't use it in production code, but I was expecting way worse when I was trying to do the multi-version import. So it doesn't need too much magic.
Okay, thank you.